Okay, now we are looking at the uniqueness of carbon, and we are saying, first of all, it forms stable multiple bonds with itself and with other elements. Yes, this is what we are saying. The uniqueness of carbon is such that it forms multiple bonds with itself. For example, when you look at carbon bonding with carbon, it can form a single bond, but it can also form a double bond. It can also form a triple bond with itself. But we have said that it can also form a double bond with oxygen. It can also form a double bond with what? A triple bond with nitrogen and many other non-metal elements. So there is a possibility of carbon to form multiple bonds with itself and with other elements, especially non-metals. We are also saying it can catenate, and we are saying catenation is the ability of an element to form chains. In fact, they can be long chains or short chains between its atoms. And what we are talking about is the ability of carbon to form long chains or chains, bonds with itself. Do you see that? So this ability is what actually brings about the variation of many compounds of carbon that in fact cause us to call it organic chemistry. And so catenation is the reason as to why carbon is able to form various compounds, because of its ability to bond with itself in a chain kind of way. It can also form branches, as long as, like for example here, I can create another carbon here, you see. So the ability of carbon to bond with itself in a kind of a chain, this is what brings about what we are calling catenation. We are also saying it forms gaseous oxides, unlike other groups of elements. When you look at sulfur dioxide, when you look at, silicon dioxide, silicon dioxide, this one is a solid. You look at silicon monoxide, it's a solid. You look at germanium monoxide, these ones are solids, germanium dioxide. These ones are solids of group 4 elements. But when you look at the oxides of carbon, you have carbon monoxide, CO, it's a gas. You also have carbon dioxide, it's a gas. All the oxides of carbon are gases at room temperature. But the rest of the group 4 elements, their oxides are solids at room temperature. We're also saying its halides are stable to hydrolysis. The halides of carbon, we have tetrachloromethane, we have trichloromethane, dichloromethane, we have chloromethane. All these ones are stable to hydrolysis. So to say, they are purely covalent and they do not dissolve in water. They do not dissociate in water. So when you look at the other chlorides, there is a possibility for them to hydrolyze in water, but those of carbon, they are stable to what? To hydrolysis. So these are some of the unique properties of carbon, apart from group 4 elements. We want to look at general properties of organic compounds. We want to look at the general properties of organic compounds. As we have said already, that organic compounds are compounds of carbon. Therefore, we have to acknowledge the first thing, that they are covalently bonded. Why do we say they are covalently bonded? Because carbon itself is a non-metal. Carbon itself is a non-metal. And also, we get to know that since the bonds are between carbon and itself, or carbon and non-metals, and therefore the type of bond between non-metals, we call it covalent bond. That's why we say most of them are covalently bonded. And because of the covalent bonding, it now determines the rest of the other physical properties. Because covalent compounds have low melting and boiling points, and they are also generally insoluble in water. And so most of these other physical properties, they so much depend on the fact that organic compounds are covalently bonded. The last property of organic compounds that we can talk about, the general property, is that most of them, their reactivities are generally slow, and most of them require catalysts, and we are saying some can be explosive, especially when you look at the combustion of organic compounds. Some, they require catalysts. Some, their reactivity is so slow, they burn slowly, but others are so explosive. For example, when you look at petrol is explosive when it is burnt in air. So, but we're saying generally most of them, their reactivity is slow. Now, we want to talk about hydrocarbons. Of course, hydrocarbons are, they constitute the biggest percentage of organic compounds. And we are saying these are compounds that contain carbon and hydrogen only. Compounds that contain carbon and hydrogen only. When you are defining the word only, is extremely important, because if you do not put the word only there, then it means there are many other compounds which actually contain carbon and hydrogen, but contain other elements. So that's why it's important for us to note that hydrocarbons must have only carbon and hydrogen. And we are going to give different classifications of organic compounds, of hydrocarbons. We are saying there are some which are saturated and there are some which are unsaturated. Saturated compounds, hydrocarbons, these ones, they have single bonds between their carbon atoms. For example, this is what I'm talking about. We can have this one here, where you have hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here, and hydrogen here. This one becomes CH3, which name is actually ethane. We say ethane is a saturated hydrocarbon. Why? Because it contains single bonds, carbon to carbon, single bonds. There are no double bonds. That's what we're saying. If we are to classify saturated hydrocarbons, all alkanes belong there. Now, looking at the unsaturated hydrocarbons, these ones, they have multiple bonds. It can be a double bond, it can be a triple bond between carbon atoms. This is what I'm talking about. Carbon to carbon double bond, carbon to carbon triple bond. This one can be this one can be called, or is called ethine. This one I can put here H2 and I put here H2. This one is called ethene. So this one is an alkene. This one is an alkyne. That's why I say that examples of unsaturated compounds have alkenes and alkynes, because these ones are characterized by their multiple bonds between their carbon atoms. Okay. Now we want to look at further classifications of hydrocarbons. We are saying we can, instead of classifying hydrocarbons as saturated or unsaturated, we can define them, we can classify them as aliphatic or aromatic. Aliphatic, these ones, they contain low carbon to hydrogen ratio. In most cases, the hydrogen content is more than the carbon content, or in terms of the number of moles. The number of moles of hydrogen are higher than those of carbon. And in most cases, these ones, they do not even have multiple bonds. And when they are heated, they burn with a non-negative flame. When you look at aromatic hydrocarbons, in this case, these ones are considered as the derivatives of benzene. The derivatives of benzene. They have that benzene ring. That's what they are called, derivatives of benzene. And their carbon to hydrogen ratio is low. When you compare to the moles of hydrogen to the moles of carbon in a molecule or in a compound, it's almost comparable. And we are saying that these ones, because of their high carbon content, when they burn with a sooty flame. When I talk about benzene, this is what I'm talking about. C6H6. In fact, it has a peculiar structure. We can draw it like this. In some other textbooks, they use a ring. But you can see that because of the benzene ring, which has a high carbon content, which is almost comparable to that of hydrogen, so we can simply say that the carbon to hydrogen ratio is high. And because it is high, that's why when they burn with a sooty flame. Soot is an allotrope of carbon. That shows that when you're burning, there's some content of carbon that is unburned. And that causes soot. But we are saying that there are also what we call alicyclic hydrocarbons. Alicyclic hydrocarbons, these ones are arranged in rings, but they have not to be benzene. They have not to be benzene. And they also, in most cases, will not have multiple bonds. For example, there is this one here. There is that one. There is this one. These ones are not just boxes, but they are extremely important organic compounds. Of course, where you see a corner, that is a CH2. For example, this one, there is a CH2 here. There is a CH2 here. CH2, and then there is CH2 here. So you are connecting the carbon atoms. And therefore the actual structure is this, but because of convenience, the iron pack allows us to illustrate without putting CH2. So we just draw the diagrams. When I talk about IUPAC, I'm talking about the International Union of Pure and Applied Chemistry. Okay. Now we want to talk about homologous series. If you remember in O-level, we so much based on what we call inorganic chemistry. And inorganic chemistry is basically the periodic table. And of course, the periodic table has groups and periods. Talking about organic chemistry, on the other hand, we have what we call homologous series. Compounds are classified in homologous series. And we are saying a homologous series is a group of organic compounds with a few of these properties. The first one you have said, it has a general molecular formula. So all compounds which have a similar molecular formula, they belong to the homologous series of that group. For example, when you look at alkanes, they have a general formula CnH2n+2. All alkanes have that general molecular formula. When N is 1, that will be CH4. Well, this will be 2 times 1 plus 2. When N is 2, that will be C2H6. 2 here, 2 times 2, 4 plus 2, 6. So this would be methane, this would be ethane. They belong to a class of compounds called alkanes, and therefore we can say alkanes is a homologous series because they have a general molecular formula. They also have similar methods of preparation because they belong to the same homologous series. So the similar methods of preparation, they also have similar chemical properties because they are almost the same, but they have some unique similarity which begins from the similar general molecular formula. I also say that they have similar functional groups. For example, when you look at alkenes, alkenes, the identical formula is CnH2n minus 2. When n is 1, that would be, no, in that case n cannot be 1 because alkenes, there is no minus 2 there. They have a carbon-to-carbon double bond, so it means we need at least 2 carbon atoms. If n is 2, that would be C2H4, and that would be C double bond C, H2 here, H2 there. I think you can see that. So you see that all these other alkenes that have this general formula, with just an adjustment of A, 2, 3, 4, 5, all of them are going to be having a carbon-to-carbon double bond. So in that case, the double bond will be the functional group. And they also say, as the homologous series are said, there is a methylene group that is added from one member to another, and a methylene group is simply CH2. For example, if we are considering alkanes, we are comparing. In that case, maybe I can compare C2H6. That is when n is 2. This one, in structure formula shall be CH3. The reason I write it like that is because every carbon must have four bonds. In that case, if I want to increase to C3, when n is 3, that will be 3. Here it will be 2 times 3, that is 6, then plus 2, that will be 8. So it shall be C3H8, and that shall be, I'm just going to add a methylene group in the middle. If I want to write the structure formula, it shall be CH3, CH2, CH3. So you see that the difference has become an added methylene group, CH2. If n is 4, that will be C4H, that will be 2 times 4, that is 8 plus 2, 10, H10. So I'm just going to get this, I just add a CH2 in the middle, so it shall be CH3, CH2, CH2, CH3. So you see that I am increasing the molecular formula or the number of carbon atoms in the alkane homologous series, but the difference between the compounds as you ascend the homologous series is a methylene group. There is no methylene group here, I've added. There is one here, I've added there. So it means if I even continue down, I'll just keep adding a methylene group. And because of addition of a methylene group, there's what we call an increase in molecular mass, because the CH2 comes with the molecular mass of 14, and therefore, because of the increase in molecular mass, it causes a slight change in the physical properties. It causes a slight change in physical properties because most of the physical properties depend on molecular mass. So if the molecular mass is increasing, then the physical properties are going to increase also. They are going to vary or to change. That's why most of the beginning compounds in a homologous series will be gases. As you continue to go down, they will be liquids, and then eventually they will become waxy solids of low melting and boiling points. Okay, now we want to talk about functional groups. Previously, I said that compounds in the same homologous series have the same functional group. Now, I want to go into details to explain what a functional group is. A functional group can be called in the most reactive site of a compound. Of course, you know, most organic compounds, because they have carbon and hydrogen in large amounts, carbon and hydrogen are not very reactive. And therefore, there must be a site on an organic compound that sparks a reaction, or that causes the organic compound to be reactive. And that's what we call a functional group. So we're saying a functional group is an atom or group of atoms that determine the specific chemical property of the elements in a homologous series. Like an illustration I can bring to relate a homologous series to a functional group. I want to compare two classes of races or people, the Chinese and the Indians. When you look at somebody, you can easily know this one is a Chinese, this one is an Indian. So you can say Chinese form a homologous series, Indians form a homologous series. The question is, what causes them to be different? What causes you to identify or to differentiate a Chinese from an Indian? So those factors that cause a difference become their functional group. So basically, that's what we're talking about. And different homologous series have different functional groups. Like we said, alkenes. When you look at alkenes, they have a carbon-to-carbon double bond. When you look at alkynes, they have a carbon-to-carbon triple bond. The double bond and the triple bond become the functional groups that differentiate an alkene from an alkyne. We also have what we call alcohols. When you look at alcohols, for them, their general formula is ROH, whereby this R can be an alkyl group. But the most important site on an alcohol is the OH group. So because of that, we can say that alcohols are organic compounds with an OH group. So all organic compounds with an OH group can form a homologous series. And the carbon OH bond becomes the functional group of that homologous series. Okay, now we want to look at some of the examples of homologous series. We look at their structure formula and their molecular formula, and we cite out a few examples. So we're dealing with alkane. We said, of course, their general formula is CnH2n plus 2. And if I want to show the structure formula, I'll need to use examples. For example, when n is 1, that would be C, then H, 2 times 2 times 1, that is 2 plus 2, that is 4. That can be the molecular and the structure formula in that case. If n is 2, of course this one we are going to call it methane. When n is 2, that shall be C2, H, 2 times 2, 4 plus 2, that is 6. H6. This is the molecular formula, but it's not the structure formula. If I want to write the structure formula in that case, I have to first create a carbon and another carbon. Of course, since they are alkanes, single bond. You have to make sure every carbon has 4 bonds. So I create 4 bonds here and 4 bonds there. So I put hydrogen everywhere. And that one becomes CH3, then also CH3. So I can write it here as CH3. And this one I'm just going to change and just call it ethane. There are many other examples of alkanes, as long as n is an integer, you just punch there, and then you can be able to come up with many other examples, as you can see. But what is so clear about alkanes is that they end with a suffix ANE, you see, ANE for methane, ANE for ethane. The next can be propane, can be butane, pentane, hexane, heptane, octane, etc. Let's look at alkenes. Their general formula is CnH2n, and these ones are characterized by a double bond. The example, of course, the double bond is between carbon to carbon, and that means that we cannot consider a compound with one carbon atom. The least can be 2. So we can have C2H4. C2H4, let's try to see how the structure formula will come about. So we have C, double bond C, that is between two carbon atoms. There's a double bond, and therefore to create more bonds, make sure every carbon has 4. I'm going to create here 2 bonds, and there are 2 bonds. So each carbon has 4 bonds, and therefore I put hydrogen everywhere, and therefore I can say that is H2C double bond C H2, and therefore my C2H4 will become H2C double bond CH2, and I call that one ethene. I'll call it ethene as the name. This one, the name was ethane. This one is ethene because the homologous series is different, and also the functional group is different. Maybe the other one I can give you is when N is 3, look at it as C3H6, because just C3H2 times 3, which is 6. And in that case, if I want to write the structure formula, I just need to first create a bond between carbon, 3 carbon atoms in this case. I create a double bond in at most 1 of them. In that case, maybe I can put the double bond here between 2 atoms. You cannot create a double bond for both. For more than 2 carbon atoms. It must be at least on 1 carbon to carbon. So we expect every compound that belongs to alkenes to have a 1 carbon to carbon double bond. Unless a compound is aromatic, but if it's not aromatic, we expect 1 carbon to carbon double bond. In that case, I can create more bonds to make sure each carbon has 4 bonds. So here I'll create 3 more. Here there are already 3. I'll just create 1. Here there are 2. I'll just create 2 more. And I put hydrogen here, hydrogen here, hydrogen here, hydrogen here, hydrogen here, and hydrogen there. And the compound will be H2C double bond CH, then CH3. But some books we can write it as CH2 double bond CH, CH3. Of course, this double bond can even come here, so it's just the same. And the compound is called propene. E-N-E. So, looking at alkynes, general formula CN H2N minus 2. H2N minus 2. A clear example when N is 2, C2H2. C2H2. Because this will be 2 times 2, 4 minus 2, which is 2. And the structure formula there is important to know that the functional group is a carbon-to-carbon triple bond. So the triple bond in that case will be carbon, triple bond, carbon. And so we have to make sure each carbon has 4 bonds. So I put here hydrogen, and then I put here hydrogen, and then it becomes HC, HC, triple bond, HC, and I call that one ethine. So the suffix here is YNE. This one is ENE, that one is ANE. Alkyl halides, these ones are of the general formulas RX, where R is an alkyl, alkyl halide. In that case, I can give an example where the alkyl halide, in that case, the alkyl is, maybe I can use a methyl group, CH3. And then the halide I can use, because halides are group 7 elements. So I can use Cl, and this one is, I can call it chloromethane. Chloromethane, because it is a derivative of methane. I've just replaced one hydrogen with a Cl. Of course, we can replace more other hydrogen with the chlorides to have dichlorides, tetrachlorides, etc. Then we can talk about alcohols as our last example. There are many other homologous series, but you can just look on this one. This one, the general formula, ROH. So the functional group is the OH. So I can make R a CH3, then OH. This one I shall call it methanol. I think you can see it is also a derivative of methane, but I have replaced one hydrogen with the OH, so it becomes methanol. There are also other examples of alcohols like ethanol, propanol, as long as the number of carbon atoms is increasing. So basically that's all we can talk about the introduction to organic chemistry. Thank you.